There are three quantities that an object undergoing uniform circular motion experiences. One is acceleration, one is force, and one is velocity. I'm going to draw two positions on this circle, right here and right here. Let's say that this object is at one point at this position and then traveling counterclockwise to position number 2. So position number 1, position number 2. I'm going to draw three quantities on here, and I want you to identify which one is which. Velocity, force, acceleration. Okay, the first one I'm going to draw is this way. The second one that I'm going to draw is this way. And the third one that I'm going to draw is this way. The green arrow, what could that represent? Which variable or variables could that represent? Okay, so let's pick one. Let's say it represents centripetal force. Okay? The centripetal force is that force that acts on an object moving in a circle, keeping it from going in a straight line. Remember, that object wants to go in a straight line always, right? But if there's a net force, an unbalanced force, then it doesn't end up going in a straight line. That centripetal force is that force that keeps it from going in a straight line that's directed toward the center of the circle. What about that blue line? What variable is that going to represent? Or which variables could it represent? Nick? Inertia, yeah, okay. Okay, it could, for sure. Inertia wants to take something in a straight line. The heavier something is, the more it wants to go in a straight line, right? What's the one I'm thinking of here, though? A numerical quantity, Dylan? Velocity, yeah. I like inertia there. That's a good answer, too. It's just not the one that I was thinking of, that's all. It's not wrong. It's just not the one that I was thinking of. Yeah, that one's definitely going to be velocity. It's not going to be acceleration. It's not going to be force because the velocity is always at a tangent to the circle. It's always a straight line, just like inertia is a straight line. What about the red one? If we've got force and velocity, then the red one's going to represent the acceleration, the centripetal acceleration. It's kind of hard to see how the acceleration can be directed toward the center of the circle, but we did a little demonstration the other day to help us to understand why the force is directed toward the center of the circle. When I swing those keys around my head, it's my hand in the middle of the circle that's providing that centripetal force. So it's pulling inwards toward the center. And if the force is toward the center, then the acceleration has got to be toward the center as well. All right. How did we calculate the value of the centripetal acceleration? You don't remember that equation, that's okay, because it's on your data sheet. But look it up if you don't remember it. What is it, Isaiah? Good, it's v squared over r. Notice we have those absolute value signs around the a. What does that represent? Ashton, what do those absolute value signs represent there? When we calculate acceleration, what are we not going to get out of that calculation? No. Not that. Well, we're not going to get time out of it. You're right, but Dave? We won't get a negative out of it. We're only going to get a positive, right? Which means that we're not going to get a direction. Is that okay? It's a vector. Don't we need direction? Well, we do. We do need direction, but we don't need to get it from the equation because we already know the direction of the acceleration. What direction is the acceleration every single time? Well, we say positive. Inward toward the center of the circle. Usually we make it a positive value, but the direction is actually inward toward the center of the circle. So we don't need an equation to tell us that if it's always the case. What about centripetal force? Real similar to the centripetal acceleration equation. What's any force? Well, okay, push or pull, but what's the equation for any net force? Mass times acceleration. So what are we going to do here, Jack? Mass times the centripetal acceleration, m times v squared over r. Okay, we had a couple of sets of homework to do last night, page 255 and 256. So are there any issues with the questions that we had on page 255? Remember that you are having a quiz on this tomorrow. So if you're like, I'm not so sure about question number 2, then now would be a great time to ask that. Nick? 2 and 3? Okay, 2 and 3 it is. 2 says a child playing with a top spins it so that the centripetal acceleration is 125, which is about 12 Gs, right? 12, 13 Gs. At the edge, a distance of 3 centimeters from the axis of rotation. In other words, that's going to be the radius. What's the speed at the edge of the top here? Some people would look at this and say, I just want to use v is equal to 2 pi r over t. Is that a valid equation to find speed? Sure it is. It's not going to help us because we don't know what the period of this orbit is of this top spinning on its axis, but it's valid. If you can find the period or you know what the period is, then you can use that equation. It's a perfectly valid equation. That's not what we're going to do, though. What are we going to do? Yep. Yeah, we're going to say the centripetal acceleration is v squared over r. Now we want to solve for speed here. So let's take the r up by multiplying. It becomes a times r equals v squared. And then we're going to square root the speed and square root the other side as well. So it ends up being the square root of a times r. So let's say square root of 125 times the radius, which is 0.030 meters. Let's do this on the calculator here. Let's say 125 times 0.03. Let's press equals, and then let's square root that. And when we do, we get 1.94 meters per second. 1.94 meters per second. Good? Is that okay? Okay, number 3 says a helicopter blade has a diameter of 14 meters. Right away, Nick. What do you see with this one that we got to pay attention to? That first sentence. Yeah, that's right. We need to divide that by 2 to get radius, right? So I'm going to circle that in red just to draw attention to the fact that there's something in there that I got to not forget to do. Acceleration is 25/27. What's the period? That's a little bit tougher, actually. We're going to say the radius here is 7.0 meters. We're going to say the acceleration is 25/27.0 meters per second squared. We're going to find the period. Tell me what you want to do first. Jackson, what do you want to do first on this one? Speed, you mean? Yeah, and using a is equal to v squared over r? Yeah, that's fine. I'm pretty sure he's right. I'm pretty sure we're going to need speed and then use another equation to find period. But even if he's not, are we doing anything wrong here? Okay, worst case scenario is we don't end up getting the answer we want, but we're not going to get the wrong answer. Don't be afraid to try this. Okay, you end up getting speed, great. If it's not helpful, oh well. If it is helpful, which it likely is, then great. Okay, let's rearrange this to solve for speed again. We get square root of a times r, which in this case is the square root of 25/27 times a radius of 7.00. Gives us a speed of, what do we get here? 25/27 times 7. Square root that. Gives us a speed of 133 meters per second. It's pretty fast, eh? Yeah, you certainly don't want to be standing there in the way of a helicopter blade as this blade propels itself through the air at 133 meters per second. Okay, that would hurt a lot. Actually, it might not hurt that much. It would be over so quickly that that you probably wouldn't feel it at all. Don't stand there anyways. Now what? Max, what do you want to do now? How do you do that? Good. That's what I would do as well. Okay, in the end, if it doesn't work, then we'll try something else, but it's valid, so we'll try it here. Rearrange that to solve for t. T goes up by multiplying, the v goes down by dividing. Whenever you have something on the bottom and the top and you want to switch places, just switch places. 2 times pi times 7 divided by 133 should give us the number that we have there, 0.331. There we go. Done deal. How many digits should it be? 3? Oh, shouldn't it be 2 digits? Because I said r is equal to 7.0 meters there. The original data was 14.0 meters. Good. The original data was 3 digits and 5 digits, actually. 3 and 5. So final answer is going to be 3. Good. You had a second page of homework to do as well. That was on page 256. Any issues with that one? Yep. All right, let's take a look at both here. Number one says the intake fan blade on a jet engine has a mass of 7.5 kilograms. As it spins, the middle of the blade has a speed of 365.9 meters per second, which is slightly faster than the speed of sound. Distance is 73.7 centimeters from the axis of rotation. I'm going to circle the centimeters. What are they giving me there? 73.7 centimeters from the axis of rotation. Where is the axis of rotation always located? In the middle of a circle. So what are they giving me there, Sebastian? The radius. Yeah, they're giving me the radius of the circle. We just got to convert that to meters. What's the centripetal force acting on the blade? All right, so let's say my mass here is 7.50 kilograms. Let's say my speed is 365.9 meters per second. And let's say the radius is 0.737 meters. Let's find the force. I think all we're going to do is the main equation here, mv squared over r. 7.50 kilograms times 365.9 squared divided by 0.737. You're going to get a big number or a small number here? We're squaring 365, right? So that means we're going to get a really big number. I mean, you got to figure. We're talking about the intake fan of a jet engine. Okay, there's going to be a pretty big centripetal force on it, right? When we do the math there, I think we end up getting 1.36 times 10 to the 6, the answer in the book. Good. Imagine if you're an engineer and you're an aerospace engineer, you're designing airplanes or something like this, and you're designing a jet engine. First of all, it wouldn't be just you. There'd be hundreds of people working on it, right? So you wouldn't be responsible for everything. But imagine, you know, you're part of the team that's designing this jet engine. Not only do you have to build an engine that will provide enough power to make an airplane go at 800 or 900 kilometers per hour, you have to design the wings so that there's enough lift force to cause it to go up. But you have to think about even little things like, oh wait, the centripetal force acting on this blade that's required to keep this blade together is 1.36 times 10 to the 6 newtons. If there happens to be a weak point, okay, a weak point on the blade, then what's going to happen to it? If it can't hold, if it can't support that much force, then the blade is going to completely break apart, right? Would it matter if there's wind? Like, yeah, I suppose so. I suppose so. Certainly, like for the structure of the airplane, you'd have to worry about that. You'd have to think about that. I don't know about worry if that's the right word, but think about that for sure. But as far as the engine goes, yeah, probably. I mean, because in the end, if there happens to be a headwind, you know, coming at it, then yeah, then I suppose the air coming in is going to be faster than the air normally would be, and therefore centripetal force might be bigger. Okay, question number 2. A .0021 pebble is stuck in the treads of a dirt bike's wheel. The radius of the wheel is 23 centimeters. Got to convert that to meters. What's the speed of the wheel here? We're going to say FC is equal to mv squared over r. We just got to rearrange this to solve for speed. How do you get speed? What do you want to get rid of first, the m or the r? That doesn't matter, really. It doesn't really matter. Okay, multiply the left side by r. Works for me. So FC times r equals mv squared. What do you get rid of next? Yep. M, we're going to do that by division. So FC times r over m equals v squared. And now what? Finally, Quinn, now what do we got to get rid of? Yeah, and how do we do that? Good. So it becomes v is equal to the square root of FC times r over m. So what do we got here for the centripetal force? 0.660 newtons times r, 0.23. Divided by the mass here of 0.0021. That's a pretty small force, right? 0.660 newtons. Why do you think it's such a small force? It's a tiny mass, right? It's a small force because it's a small mass. Think about that. An object that is moving wants to keep moving in a straight line at a constant speed. This pebble wants to keep going at a constant speed. What property of this pebble, of this little stone, wants to keep it going in a straight line? What's it called? Inertia. Inertia wants to keep it going in a straight line. What's inertia dependent upon? Mass. So the less mass, the less inertia, the less tendency to stay in a straight line, therefore the less centripetal force required to keep it going in a circle. Make sense? The more mass, the more inertia, the more tendency to keep going in a straight line, and therefore the more centripetal force would be required to keep it from going in a straight line. All right, let's calculate this now. Let's say 0.66 times 0.23 divided by 0.002. Now let's not forget to square root that. When we do, we should get the answer in the book, which is, I just got 8.7. What did you guys get? What did I do wrong? What, 0021? What did I make them as? Oh, yeah, okay. Yeah, okay. I divided by 0.002. So if we do it by 0.0021, then I'm sure it probably is going to work out to be right. 8.5 was it? Good there? Okay, let's do one more example here. So it says, determine the maximum speed at which a 1,500 kilogram car can round a curve that is a radius of 40 meters if the coefficient of friction between the tires and the road is 0.6. Notice it's actually static friction. Static friction would be like a rolling friction. It's what keeps an object from beginning to move. But remember, when an object is rolling, it's not actually moving relative to the ground. Right? Sliding would be kinetic friction. Okay? Unless it's sliding, then each point on the tire isn't actually moving. So when you're driving your car, it's actually static friction, believe it or not, that's keeping you on the road. Ironically, it's static friction that even gets you moving in the first place. No, when you begin to move, it's static friction. That there's definitely static friction there, but it's static friction that's getting you moving. It's kind of weird, right? Like we say, it's so counterintuitive because static friction is what keeps you from moving. But in the case of when you've got a wheel turning, it's actually static friction that gets it moving, right? If you take a look at this, okay, let's say this is my wheel, and let's look at this one spot where the label is. I don't know if you can see that, where the label on the marker is. Okay, right now, hey, I go to turn my wheel. That spot doesn't move. It doesn't move relative to the ground here. It doesn't slide. So that's actually static friction. We want a lot of static friction between the wheel and the road when we're trying to get the car moving, ironically. If we're trying to slide it, we wouldn't. But if we're trying to roll it, we do. All right, what are we going to do here? We know that if the object is going in a circle, there is a centripetal force, right? What did we say yesterday about centripetal force? It's never fundamental. What do we mean by that? What do we mean by that if I say the centripetal force is not fundamental? It's always caused by something. When I swung the keys around my head, what was the centripetal force caused by? My hand. When the Earth goes around the sun, what's the centripetal force caused by? Gravity. When the electron orbits around the nucleus, the centripetal force is caused by an electric force. There's always another force that we just call the centripetal force. In this case, when a car is going around a turn, there's a centripetal force. But what is it really that's providing the centripetal force? Friction. Friction is the centripetal force here. Okay? Centripetal force doesn't exist on its own. It exists because friction acts between the road and the tire. So what I want to do in this question is set the centripetal force equal to the force of friction. I can do that because it's the force of friction that's causing the centripetal force. There's always something causing it. In this case, it's friction. Sometimes I'm just going to set Fc equal to mv squared over r because I don't know what's causing it, or I don't care what's causing it. Sometimes, as in this question, we're going to set them equal to each other, which I can always do if I know something about both of those. mv squared over r equals mu times the normal force. What's the normal force equal to if on a flat horizontal surface? Yeah, mv squared over r equals mu times m times g. Now, if the road is banked, which most turns are banked a little bit, well, then the normal force becomes a different value now, right? So the analysis becomes a little bit trickier then. Well, let's assume it's a flat surface, though. Masses cancel. What does that tell us if masses cancel? You're driving around a turn. It doesn't matter how heavy your car is. You get those 8 people in the back of your Datsun. It doesn't matter. You're going around a turn, it's not going to make any difference as far as friction goes, whether you have 8 people in the back or 1 person in the back, because the masses end up canceling. All right, v squared over r equals mu times g, and we're looking for v. So let's take the r up by multiplying, and then square root the v. Mu g r. Mu is 0.60, g is 9.81, and r is 40 meters. Let's do the math on that one. Say 0.6 times 9.81 times 40 gives me 235. Square root that, and we end up getting 15.3. Should just be 15, actually, shouldn't it? 2 digits because of this. So look, what happens when you go 14 meters per second? You stay on this road, no problem. What happens when you go 16? You fly off. You go off, right? Now, if there was ice on this road, the coefficient of friction would be lower. And if the coefficient of friction would be lower, then the maximum speed would be lower, right? All right. Let's take a look at the questions that go along with that on page 259, please. All right, let's have a look at question number 2. It says, automotive manufacturers test the handling ability of a new car design by driving a prototype on a test track in a large circle at ever-increasing speeds until the car begins to skid. And why would the car begin to skid? Well, because friction provides the centripetal force, but at some point friction can't provide any more centripetal force, and therefore the force that's required to keep the car out of a straight line and going in a circle can't be provided by friction. So the inertia of the car takes over. The inertia of the car wins. Prototype car, 1,200 kilograms, tested and found to skid at a speed of 95 kilometers per hour. What's the coefficient of static friction between the car tires and the track? Want to convert that to meters per second, so let's circle that. What do we got here? A radius of 100 meters. We got a mass of 1,200 kilograms. And we got a speed of, what is that, 95 kilometers per hour? Multiply by 1,000, divide by 3,600 gives me 26 point what? Let's go more decimal places, isn't it? Okay, good enough. What's the coefficient of friction? We're probably going to do the same thing as we did in the example problem here. Fc equals FF. Now, it's okay just to say Fc is equal to mv squared over r. It's okay to say F is equal to mu times Fn, the normal force. Both of those equations are perfectly valid, but it just seems to me like we're going to end up using both, so we might as well set them both equal to each other right away. mv squared over r equals mu times the normal force, which is m times g. Mass cancels. I want to solve for mu, take the g over by dividing. So mu becomes equal to v squared over r times g. Now my speed is not 95, rather it's 26.3889. Don't forget to square it. Divide it by r, 100 meters times 9.81. And when I do that math, it should work out to be 0.710. Is that a reasonable coefficient of friction? Sure it is. We usually see that range of 0 to 1, right? Can occasionally be a little bit higher. Usually in that range of 0 to 1. This falls nicely in that range. All right. All right, one more little thing here, and then we'll give you a break for a couple minutes. I want to talk about centrifugal force right now. We've talked a little bit about this yesterday, but we didn't call it centrifugal force. Centrifugal force is that force, and I'm going to put this in quotation marks. You'll see why in a moment here. The force pushing outwards on an object moving in a circle. You guys have all experienced that before, right? Yeah, 2 days ago when you were riding the roller coasters on a field trip, you experienced the centrifugal force, that force that pushed you outwards. You guys know that when you go around in a circle, I talked about this yesterday with the Datsun and my baseball coach when I was a kid. That centrifugal force that pushes you out to the outside, right, to the outer wall of the car. We've all experienced that at one point or another. You're riding that ride at Callaway Park where, I can't remember what they call it, but it spins around and you get pinned against the wall. Okay, the centrifugal force pinning you against the wall, pushing you outwards and pinning you against the wall. Well, the centrifugal force on the keys, for that matter, causing these keys to be pushed outwards toward the outside of the circle. I spin it around faster. You know that it goes further out. The centrifugal force is bigger, right? Here's the problem. It doesn't exist. And that's why I put force in quotation marks. The centrifugal force doesn't exist. That force that pushes you outward, despite the fact that you have felt that force, it doesn't exist. So what, are our bodies just adapted or evolved to feel this force that doesn't really exist because our ancestors knew that something or another? And I don't know. How do we feel a force that doesn't exist?
Because let's say we're going in a circle,
Yep.
turn or something.
Yep.
We want to continue to go like what we're supposed to go, but something pushes against us. So it's not us feeling a force.
Good.
Something pushing against us.
That's exactly it. That's exactly it. Whenever there is an acceleration, and there is an acceleration here, right? When you're going in a circle, there's a, what do you call it? A centripetal acceleration. There's an acceleration directed toward the center of the circle. Whenever there's an acceleration, you feel what we call a pseudo force, a fake force. Always. Always. It acts opposite to the way the acceleration is. Let's say that you're sitting at a stoplight in your car and you're in a little bit of a rush. So when the light turns green, you put your foot really quickly down on the gas pedal and you accelerate quickly. You feel yourself being pushed back against that seat, right? Are you being pushed back against that seat? Not at all. You remain at rest. Really, it's just your inertia. Your inertia wants to keep you at rest, but there's an acceleration forward, so you feel a pseudo force backwards. Whenever there's an acceleration, you feel a pseudo force opposite to that acceleration. When you're going around in a circle, there's an acceleration toward the center. You feel a force away from the center, but it's not a real force. It's a pseudo force, a fake force. The centrifugal force doesn't exist. Question? Yep. Yep. Yeah, you feel, in a case like that, you feel like you're being pushed upwards, right? But you're not really being pushed upwards, right? You're accelerating downwards, which gives you the sensation of experiencing a force upwards. Yeah, it's similar, except it wouldn't be described by mv squared over r because it's not a circle, right? Okay, well, let's hear it. Good question. So you're not against the wall. So when you're against the wall pushes you inward, which makes you feel like you're being pushed outwards, right? Because you're accelerating inwards, right? Makes you feel like you're being pushed outwards. But you're not against the wall. Okay. Let's say you jump. You're not touching anything, but yet you still end up going out to the wall. Well, how is that possible? If you like, how is it possible that you end up going out towards the wall if you're not touching anything? And you just get pushed Just if you're not getting pushed out towards the wall. Yeah, you got it. So here's the circle. Okay, let's say it's ice inside there, or you're not actually touching anything. You're moving with the circle, though. Okay, so let's say it's going, say, counterclockwise right here. Okay, let's say there's a spot right here on the circle that's painted green for whatever reason. Okay, somebody put this big splotch of green paint on the wall of this thing, so you can look at this spot and tell where that spot is at any given time. Now let's say that you are right here. This is you. Okay, you're not touching anything, or if you are, it's ice, so it's really, really slippery and there's essentially no friction there, right? Which way are you going? Which way are you going, Nick, at this moment in time? Not over the entire revolution, but which way are you going at that one specific moment in time? Straight line. You're moving in a straight line. You're moving this way in a straight line. So what happens? You go in a straight line, right? But what happens by the time you get out to this wall? This green spot, you're standing inside here looking at this green spot. And you see that, and you feel yourself being pushed out to that green spot, right? You're not being pushed out to that green spot. You're going in a straight line, and you end up going out to the wall, and guess what? During that time, the green spot caught up with you. So you perceive yourself as being pushed out to that green spot, but it's really just like it was when I was sitting at a stoplight and then put my foot on the accelerator. My inertia made me feel that force backwards, that pseudo force backwards. Here, my inertia, this time I'm moving inertia, straight line, okay, takes me to the outside, makes me feel like I'm being pushed to the outside. Make sense? You're not being pushed to the outside. You do go to the outside, but you're not being pushed to the outside. It's your inertia that takes you to the outside, just simply in a straight line. Does that answer your question? Yep. Why is it hard to resist it? Well, it's not if you're really, really light. Okay. But remember what inertia is. Inertia is dependent upon mass, and it's defined as the tendency to resist a change in motion, right? Tendency to keep doing what you're doing. So if you've got lots of mass, okay, I weigh about 155. Okay? I don't have a ton of mass. Lots of people have more mass than I do. Okay? Lots of people have less mass than I do. Okay? But I weigh 155 pounds. Okay, that's enough to provide quite a bit of inertia. So I have a tendency, a pretty good tendency to keep doing what I'm doing. So as I'm put my foot on the accelerator, I have a strong tendency to not go anywhere. So the car goes forward, I stay where I am. Why is it hard to resist? Because I'm heavy. I weigh 155 pounds. I have a lot of inertia. Similar right here. Why is it hard to resist this? Well, because I have 155 pounds of mass. I have a tendency to keep going in a straight line, and it's hard to resist that. Of course, it depends upon how fast you're going, right? Make sense? Yep. Yeah, absolutely, absolutely. The more people you have in a car, I mean, look at Newton's second law. Okay, Newton's second law, which is it's just related to inertia. Okay, because when there's zero acceleration, then you're in equilibrium, right? Translational static equilibrium. But let's say that there is an acceleration, so you're not in equilibrium. Let's say that force is constant. Let's say the car is required or is able to apply a certain force. And that's regardless of how many people are in the car. But the more people you have in a car, the bigger the mass is, right? The bigger the mass is, the smaller the acceleration will be. Okay? You notice this, right? I remember last summer, my parents came to visit last summer. Well, when we took my parents out to Columbia Ice Fields in the back of my van. So there's the four people that are normally in my family, myself, my wife, and my two kids. And now we've got an extra 300 pounds in the back of it. Make a difference? A little bit. Yeah, it does make a little bit of a difference. So we're going from a couple thousand pounds now to 2,300 pounds. Okay, it's making a difference of 15%. It also makes a difference in fuel economy. Okay, think about that. Okay, the inertia, the van wants to remain at rest. Okay, so it does until you apply an unbalanced force. It requires a bigger unbalanced force because the mass is 15% bigger. Now, I don't think it added 15% onto the fuel, but it added some on the fuel. It cost me more to drive 6 people out there, 7 people out there, than it, sorry, 6 people, I guess it was, than it would to drive 4 people out there. Oh, absolutely. Yeah, absolutely. Because when you drive separate vehicles, now you have to, now what in effect what you're doing is accelerating not 2,000 kilograms or 2,300 kilograms, but rather 4,000 kilograms. So it requires even more fuel to do that, right? Good. All right. So it's this centrifugal force thing, this force that pushes you outwards, it doesn't really exist. There's one word that we can say that it really is. What is that one word? Inertia. Okay, that's what it really is. It's inertia. Okay, the tendency to keep doing what you're doing. You're going in a straight line. That makes you feel as if you're being pushed inwards. If you happen to be at the outside, or next question, if you happen to be somewhere near the middle of the circle, you feel like you're being pushed out to the outside. But really, again, you're just going in that straight line. It's just your inertia.